Hello, welcome to this lecture on nuclear fusion as a possible energy source. My name is Nordlund. I'm a professor at the University of Helsinki, Department of Physics, and I have been dealing with fusion research for about 20 years now. I'm also a quite active member in the European Fusion Research Consortium Eurofusion, which deals with the basic research component of the European fusion developments. So what I will be talking about is fusion, the way the energy is produced in the sun, but especially about whether we can manage to get this fantastic energy source into practical use here down on Earth. So to start from the very basics, all normal materials consist of atoms. And these atoms, if you look inside the atom, so to speak, contain a nucleus in the center, a very small nucleus, and around it are the electrons. The nucleus in turn consists of protons and neutrons, heavy particles. And these atoms, they are what we start, of course, when we start to try to achieve nuclear fusion. But for nuclear fusion, we really need to go to the nuclei themselves. So nuclear fusion means a process where you take light element atom nuclei and smash these into larger, heavier elements. And if we do this for two light atoms, say hydrogen, helium, lithium, some light elements, and smash them together to a larger atom, which is stable, this process releases quite a lot of energy. And this a lot is really a lot. If we compare this with a corresponding chemical reaction, this energy release, so although there are a million times more than the chemical reaction energy release. And also, if we compare this to nuclear fission, which is used in current nuclear power plants, this is also much more efficient if you consider it per mass. In nuclear fission, heavy nuclei are split into lighter elements. So that's sort of the opposite process, and as you know, is in regular use now. But then nuclear fusion is in principle well known, and with particle accelerators it can be achieved quite easily and has been achieved since the first half of the 20th century. But why don't we have then nuclear fusion already as an energy source? Well, the reason to this is that to get nuclear fusion energy, one not only needs the light elements, but one needs to heat them up into a very high temperature. And this very high is really astoundingly high. We are talking about of the order of 10 to 100 million degrees C. Or degrees Fahrenheit for that matter. If you use an energy scale, we still have the same order of magnitude. And the reason to this is that the nuclei, they are all positively charged, and because they are positively charged, two positive charges from basic electrostatics repel each other, and hence it is quite difficult to get them together. But if one can achieve these high temperatures, and in the moment I will talk about the other requirements, then one can start achieving nuclear fusion. At these high temperatures, of course, normal materials are not stable. As you probably know, normal materials melt somewhere around 1,000, 2,000 degrees C. So at these very high temperatures, they are molten and gasified, and in fact are a state of matter known as a plasma. In a plasma, the nuclei and electrons are completely separated from each other, moving essentially freely between each other, and it is in this state when we need to be to possibly achieve nuclear fusion. Well, if you look a bit more in detail what's really required to achieve the nuclear fusion, we need to consider something which is known as the triple product of three quantities. So first of all, we must have a high enough temperature for the nuclei of the atoms. Then the density of them must be high enough. That is, we need to have enough of them in a small enough volume. And the third requirement is that we need to have them at this high density for a long enough time. This is known as the confinement time. which is really a crucial concept in nuclear fusion. And the triple product is then the product of these quantities, the temperature times the density times the confinement time. And this product, as a first approximation, determines the efficiency of fusion reactions, how much fusion we get in a given time. Well, in the sun is a big fusion reactor, very big, obviously. And in the sun, this works thanks to the fact that we have very high density due to the high pressure in the core of the sun. And the confinement time is extremely long, billions of years. As you know, the sun has existed for 6 or 7 billion years by now, and will exist at least as long more. Thanks to the fact that this density and confinement time are very high, the temperature is around, doesn't actually have to be all that high. It's of the order of 10 to 15 million degrees C. Well, that's a high temperature as well, but in fusion terms, actually not so high. Well, if you try to do fusion on Earth, obviously, if you want to do it on a time scale of interest to humans, we can't wait billions of years. So we have our confinement times by necessity are shorter. So instead of having this high confinement time, we need to have even higher temperatures. So instead of 10 or 15 million degrees C, we need to have even higher temperatures, around 100 million degrees C or even higher than this. And this is the main reason why fusion is challenging, because obviously it's not easy to achieve these kind of temperatures in any kind of a controlled manner. Okay, so the other question, in addition to the high temperatures, is of course which elements we should choose for achieving fusion. Out of all the elements which exist, the lightest one is hydrogen. And as I mentioned in the beginning, fusion works for light elements. Well, but if you look a bit closer at this, hydrogen has 3 isotopes. The basic one is the regular hydrogen isotope, consists of a proton and an electron in orbit around this proton. But in addition, there are 2 rarer isotopes of hydrogen. One is deuterium, abbreviated D, which consists of a proton and a neutron, and then the electron around it. And then there is still tritium, which consists of a proton and 2 neutrons and an electron in orbit around this. Chemically, they behave identically, except for a mass scaling difference, but from the nuclear properties, they can be different. Out of these 3 isotopes, deuterium exists in huge amounts in all normal water contains deuterium, so there is no problem in getting deuterium. Tritium is not stable, it decays after a while, and because of that it practically doesn't exist in nature, but it can be produced by several nuclear reactions, for instance from the quite common element lithium. And the easiest fusion reaction to achieve is the reaction between deuterium and tritium. This is the one which basically has the highest probability for relatively low kinetic energies. And if one achieves this reaction, that is one deuterium and one tritium coming in, when they fuse, they have a reaction, they form a helium nucleus, also known as an alpha particle, with 2 protons and 2 neutrons, then 1 neutron flies off. And most important, it releases an energy of about 17,600 kilo electrovolts. This kilo electrovolt is the common energy unit used in all atomic and nuclear physics. And this energy is actually very high. If you look at the energy balance of this reaction, to get the maximum probability of this reaction is achieved for a total incoming kinetic energy of 70 kilo electrovolts, and then we get this 17,600 kilo electrovolts out. So we see that the energy production is very big, about a factor of 250, comparing in and out energy. Moreover, if you compare this to a chemical reaction, if you take the same deuterium and tritium and make a regular chemical reaction to form the DT molecule, we would release only a few electrovolts of energy. So this reaction produces 4 million times more energy than the corresponding chemical reaction. And this is the basic reason why nuclear fusion can be of energy production interest, because you really do get a lot of energy out for relatively little energy input. So in principle, we can start achieving this. But the crucial question is that how can we get a high enough confinement of the plasma, that is high enough triple product temperature times density times confinement time. Well, there are different options for this. In the sun, the solution is to have a huge mass and which leads to a huge gravity, and then leads to this very large confinement time. And this, of course, works very well, as we know, especially on a sunny day. We can feel it, but doing this is having this huge mass is obviously completely impossible on Earth. The by far most studied way of achieving this is so-called magnetic confinement. That is using strong magnetic fields to control the movement of the plasma, to make a sort of a magnetic bottle where they stay inside and are confined. And this is what I will be talking about in the remainder of the lecture, the magnetic confinement fusion solutions. There is also something known as inertial fusion, where the idea is that the fuel is put into a small pellet and then use a very high intensity energy ray, typically a extremely high power laser, to compress this hydrogen inside the pellet to an extremely high pressure and temperature. And this leads to fusion power, but then the whole thing blows apart, and one has to bring in a new pellet to be able to continue this reaction. I mean, this does work on a lab scale, and it does produce some energy, but it's still very, very far from practical energy production due to several issues with this production method. One of the main issues is simply that the lasers, right now the lasers need to be charged for hours before one shot, and after that one has to wait hours before the next shot, which makes it very impractical, at least so far, for energy production. But as I said, the most studied concept is the magnetic confinement. In this, the idea is to use strong electrical magnetic fields, that is some sort of system of coils and electromagnets to confine a plasma. And the basic idea to achieve a confined plasma is very simple. One can have two coils surrounding a cylindrical container, and this already is enough to keep the plasma quite well inside the cylinder without touching the walls very much, and one can move the plasma along the cylinder. But if you would only consider having a cylinder, the cylinder has the problem that, of course, it has to have ends somewhere. And it turns out that even if one can have the plasma inside the cylinder, at the ends there would be huge energy losses or losses of particles from the plasma into the walls. And the question is, how can one go about solving this? Well, the easy solution for this is to take the cylinder, bend it around its central point and then match it at the ends to form a torus. And this way we get rid of the ends. There are no ends anymore because we just joined the ends. And this is the basic idea of what's known as the tokamak. This name means a toroidal chamber with magnetic coils. It comes originally from the Russian, but is now used worldwide to mean these torus-shaped fusion machines. Looking a bit more detail at it, one needs to have at least two sets of coils. In this picture, the red coils produce the cylindrical magnetic field or bent cylindrical magnetic field, and then the other coils, so-called poloidal coils, which are used to shape and control the plasma. And the gray walls in the picture are metal walls used to confine the hydrogen gas before the plasma is ignited, and also to keep impurities from the surrounding atmosphere from entering the plasma. And when this is operational, the plasma is extremely hot in the middle and then colder on the outer sides of the torus. Well, that was a schematic picture. Here is a picture of the biggest tokamak which now exists, known as the Joint Energy Torus Jet in the UK near Oxford. And as you can see from this picture here, it's quite a big machine. You see a man standing here, so you see that the whole machine is something like 5 meters tall on the inside and with quite big dimensions. The reasons they need to be big are related to the confinement time. In a too small machine, the confinement time wouldn't be sufficient. This schematic here illustrates the setup of the different coils, and also that there are many other components, vacuum pumps and diagnostics and so on, which are all needed for practical operation of such a machine. And this machine is working, and it is producing fusion reactions. And here is next is a video from a real event at JET, which was run in some years ago in an energy-producing event. This is a typical case where you see that from the colors you see the shape of the tokamak. The colors mostly come from the outer edges. The fusion plasma itself is invisible, but what you do see is the edge regions of the plasma where it is cooling down. And this is in real time, so the real fusion run in this case took about 20 seconds. And these are typical cases which have been run in the thousands at JET and many other tokamaks in the world. So we can achieve fusion in these tokamaks for sure. But this is still not a power plant. That is, to build a fusion power plant which does not yet exist, one would need to have this fusion burn here, burning at a high enough power for a long enough time to heat up a hot fluid, which could simply be water, possibly something else. And this hot fluid would then run to a heat exchanger. The heat exchanger would heat up another round of water, and this water would then run turbines, which then would produce electricity. The water could also be used actually for direct heating by remote heating of houses or factories or something else. So this is the basic idea for a power plant. In here, the exotic part is the left part, the fusion part. The rest is conventional technology. That is all regular heat power plants, coal-fired power plants, nuclear fission power plants run with this kind of a heating cycle. So this part here is certainly very much working technology. But the challenge remains how to get this fusion to work efficiently enough, long enough and reliably enough. And in terms of how well it is working, there has been huge progress in trying to achieve fusion. If in the early 1970s, the fusion efficiency was still horrible. One could get 1 watt of energy out by 1 megawatt of heating. That is, the energy production was 1 part in a million, which obviously is not very good. But these points here in this graph show how the fusion triple product has increased with time, and also how the central ion temperature has increased. So you see, starting from the 70s, from quite inefficient machines, in the 1980s and 1990s, several very efficient machines have been built. The JET, also the JT60 Torus in Japan, several machines in the US and other machines in Europe. And together these have come to quite high triple products, which start to approach the one needed in a fusion power plant. And the best shots at JET have almost achieved the break-even. That is almost same amount of energy out as energy that was put in. Right now, what is happening, the main development in the field is the construction of a tokamak known as ITER, which is really a way forward to an almost power plant size machine. The projection is that ITER would work here at the edge of a power plant, and once ITER is working, one would need only a very small step more to get to the power plant scale. And ITER is currently in construction in Cadarache in South France, about 50 kilometers north of Marseille, in a quite beautiful French countryside. It's being constructed. This here illustrates an existing research site that is nearby, and this is the ITER site which is now being built. It's built by a completely international consortium where basically all the big powers in the world have joined their efforts in trying to build this machine. And this is now is under construction. It takes quite a while. The main reason is that it's really a unique machine. Nothing like it has ever been built, and there have been big challenges in with just the engineering point of view, how to build these huge metal components. In this schematic, you can see a person here. So you see it's something like 20 meters high. The walls are of the order, the whole construction is of the order of 50 meters high. So it's really a very, very big machine, which all needs to be built stably and very reliably to enable a safe and reliable operation of the machine. But still, it's now quite well underway, and it's hopeful that it will be finished in something like 5 to 10 years from now. After ITER is built, there are already planning going on for really a power plant, fusion power plant known as DEMO, which is now in the preliminary design phase. So, how certain is it that ITER will actually work and that DEMO will work as it should? Well, the plasma physics part of it, that is how well do we understand the plasma, how well can we control it for energy production. In this respect, most people are quite optimistic and that it's considered almost certain that ITER will produce energy by something between a factor of 10 or 20. Some people are optimistic and saying even more, but the official aim is to produce energy by a factor of 10. DEMO in turn would be designed to produce energy by a factor of 50, suitable for commercial energy production. So why is this taking such a long time, and why isn't it? Why aren't there many fusion power plants constructed yet? Well, it is difficult to build such a big machine, although the basic idea is quite clear. There are major challenges in many engineering practical points of view. And these are now what's currently being settled for ITER. The other big issue, and this is really where there is still scientifically uncertain questions, is which materials to build ITER and DEMO from. Well, ITER, it's known what it will be built from. And it's known that it will operate well, at least for several years, with these materials. But still, it's not guaranteed that it will work for a very long time, very well, without having to replace some parts. There are many reasons to this, but the main reasons are that the helium coming out from this plasma needs to be pumped out to enable long-time operation. And although the helium is cooled down, it still affects the wall materials, inner wall materials to some extent. Also, the side materials need to be cooled during operation. They are heated up by the hot plasma, and they need to be cooled and without having too high temperature gradients, which would make materials break. And this is also which needs development of new metal composites to achieve this. And finally, especially in DEMO, not so much in ITER, but especially in DEMO, a power plant scale, there will be lots of neutrons produced, and these will affect the structural materials and degrade their mechanical properties after many years of operation. And these all are issues which are currently now being tackled in the Eurofusion Consortium worldwide in many research groups, and I personally am quite optimistic that we can solve these things, but we are not quite certain, and that's why we need this ITER machine and a test power plant DEMO to settle how exactly to select these both the engineering and the materials choice issues. At the same time, also the plasma operation, we can't be 100% sure it will work as designed before we have built it. There are very advanced computer models for this, but the computer models need experimental testing, and the only way to test them fully is to build a full-size machine to test them. And just as a final technical point of view, I'll give an example of what these materials challenges are from our own research in my group. What we have been doing is looking really how the helium and hydrogen coming from the plasma affects the bottom part of the plasma and the bottom part of the plasma and the materials surrounding it. This is really a complex feedback process where particles escaping the plasma will affect the materials, and the particles coming out from the materials will affect the plasma, and this will go in a circle which needs to be fully understood. And in the animation here, what we see is a deuterium coming in to a beryllium carbide material here, and this beryllium and carbon atoms in this particular case erode in the form of a small molecule of beryllium carbon 2 hydrogen molecule, which then enters back into the fusion plasma. And this will probably break in the fusion plasma, but will affect the edge plasma properties, which needs to be taken into account in the plasma physics models to understand and control the plasma operations fully. So from this talk, you may have gotten the idea that this is not quite easy to achieve, and actually it is very, very difficult. It is a big challenge. So why should we do it if it is so difficult? Of course, there are other ways to produce energy already on Earth, which are working quite well. Well, the main reason is that fusion, if and when it's gotten to operate reliably, it will produce very large amounts of energy, and from fuel which would last very, very long. That is, deuterium will exist as long as there is water on Earth, so that's certainly a long enough time for mankind. Tritium can be obtained from lithium, which is a quite common element in the Earth's core. As you know, used in regular lithium-ion batteries in computers and mobile phones and so on. So tritium can be obtained in copious amounts. So the fuel can certainly say that we would have enough fuel for at least millions of years from nuclear fusion. The other thing, which is the biggest advantage compared to nuclear fission, is that nuclear fusion is very safe. Any disruption in the operation will stop the reaction within seconds, and that is a short enough time that there wouldn't be any explosion, there wouldn't be any leakage of radioactive material to the surrounding or anything like this. This relates to the fact that the plasma is not so easy to control, and any significant instability in the plasma will make the fusion reaction stop. And the worst thing which can happen is that some of the materials on the inside of the reactor may melt a little bit, but this is nothing dangerous for the environment. A third major reason is obviously that there are no harmful greenhouse gases produced. The output is helium, which is a completely harmless noble gas. And related to this is that it won't produce any long-lived radioactive waste. The reaction itself doesn't produce any radioactive materials at all. Inside the reactor there would be a little bit of neutron activation, but this is much smaller than in current fission reactors, and the materials can be chosen in a way that there really is no long-lived radioactive waste coming out. So the other remaining question is, when could this become as important energy source? Unfortunately, development of fusion has taken a long time, and it is still taking time. These are complicated machines, and the worldwide funding level is still relatively low compared to how much is spent, say, on coal or oil or something like this. Even in the best projection, it looks like nuclear fusion energy could really become a significant production of electricity to the regular grid sometime around the 2050s. But from then on, if everything goes well, it could start growing quickly. This is one projection how nuclear fusion could become a significant part of our electricity production compared to a wide range of other sources. These kind of predictions are of course highly uncertain with respect to not only nuclear fusion but all of these other kind of energy production sources, because for instance gas production, oil production has not always progressed as one might expect. But still, it is quite possible that in the second half of this century, nuclear fusion could really be a significant energy source. This may sound as a long time, but we have to remember that energy production, already regular energy production, works with very long time scales. In Finland, there is a nuclear fission power plant, Olkiluoto 3, which is currently under construction. In the design, it's said that it will be operational until the 2070s, 60 years in the future. So it is in no way exceptional to be planning for long times ahead with respect to energy production. And of course, we all hope that mankind will have enough energy around 2100, whatever the sources are. So this is really something which is worth putting efforts to and is worth working on, even though it is difficult. So to conclude, I hope that this very short introduction into a complex field gave you an idea that nuclear fusion is one of the very few possible future energy sources which could produce energy for millions of years with enough fuel and enough resources to last for a very long time without causing any significant environmental problems. Of course, another source which could last for extremely long times is solar energy itself. And in this respect, it's sort of politically interesting that the sun's energy is produced by nuclear fusion. So most certainly world energy production will rely on heavily on different ways of nuclear fusion, either from the sun or produced here on Earth. And right now, the ITER machine, which is under construction, will provide a good knowledge of how to control a plasma for large-scale energy production. And at the same time, it's a very good machine to test all the engineering challenges which we need for doing really practical fusion power plants. And the next stage, demo, which we're already working for, could pave the way for fusion energy production from the 2050s on. The timescale here is largely determined by international funding levels, how much the governments and research organizations are willing to put efforts into fusion. Could fund faster if there is an increased level of fusion projects and fusion funding, and vice versa. With decreased funding, it will certainly take longer. There are major challenges for long-term operation. Most of these are actually related to the materials choice. But we are working in my group, and thousands of other research groups around the world are working to solve these materials problems. And I'm personally quite hopeful that we will find good solutions to all of them within a decade or two. Thank you for your attention to this lecture.